We don't see too far. No, we never did. Every circle of sight has a place where vision ends. They place a sphere beneath your feet, turn the other man around, both looking through a hemisphere from opposite sides of the ground. They point toward a distant light and tell you what you saw, but seeing one bright point at night doesn't resolve its source at all. We don't see too far, despite the lies they tell. Every circle of sight fades where conditions fail. Angular size and contrast fall, the light must reach the eye. Brightness, ground, and atmosphere define the edge of sight. No curvature required, just the limits of the light. Personal dome deceivers come to twist what vision means. They claim the air invents a world that isn't physically seen, but every viewer holds the center of the field they can observe. Perspective pulls the features in until they finally emerge. Resolvable doesn't mean available. Detectable doesn't mean resolved. One point of light cannot reveal the shape that made it glow. The first failed condition defines how far we go. We don't see too far, despite the lies they tell. Every circle of sight fades where conditions fail. Roughly 125 miles for observations from the ground, under the best conditions before the image breaks down. No curvature required, no unrestricted sight, only distance and perspective and the physical limits of light. We don't see too far. We see until the image disappears, until the contrast fades, until the light is no longer there.
Well, dreams, they feel real while we're in them, right? It's only when we wake up that we realize something was actually strange. Let me ask you a question. You never really remember the beginning of a dream, do you? You always wind up right in the middle of what's going on.
I guess, yeah.
So how did we end up here?
Well, we just came from the,
Think about it, Ariadne. How did you get here? Where are you right now?
We're dreaming?
You're actually in the middle of the workshop right now, sleeping. This is your first lesson in shared dreaming. Stay calm.
Welcome to the Real Flat Earth Friday. How are you doing this evening, brother?
I'm excited, and it's great to see everybody in the chat. Thanks for tuning in, and everybody that's checking this out on your own time. Good to see you too.
Yeah, so fun topic tonight. We are going to be talking about the real circle of sight. Now, if you go Google circle of sight, you probably won't find anything on it. You'll probably see some gun sights and some other stuff not related to our true circle of sight. And we're going to be comparing that of the Globers circle of sight. They think that they can see trillions, quadrillions, light years away. And then there's one other group that has a claim that the pressurized pizza domers say they have atmospheric domes around them. And then there's us, where we say Earth's a stereographic biblical virtual reality, in that the luminaries are being rendered to us as sky features, and that they're actually rotating around each observer, rising from the plane and setting into the plane. So we're going to really be breaking down those three different views tonight and showing which one comes out on top, which one's real.
Right? So, there's many different, deceptions that we uncover. And just like everything else, you've got flat earthers running around saying, we see too far. And the Globers are like, oh, no. They're like, we see too far. Then you got both of the two disinformation campaigns going on where they're canceling each other out, like you had said. So NASA and, modern heliocentrism, that was born out of the Vatican, they say they can see trillions upon trillions of light years to the distant reaches of the, the universe through redshift, which was debunked. Right. And then the flat earthers say, well, we can see too far. The curvature should be actually, blocking the Earth, Earth bulge should be blocking our view to these different observations. And when you actually go out and test and measure and, zoom in on distant objects like the, lighthouses or CN towers, you will notice there is a distance to the vanishing point, your horizon. And then starting to understand that what happens if something is up in the sky, like a plane, sometimes the moon, the sun, and different stars and things like that. Why is it that they don't set, but sometimes they just fade out of view? So tonight, Jason, you've prepared an excellent, presentation so that we can actually start to understand why are we not able to see forever? What is actually happening with the way that our eyes work, and basically all different cameras, anything that has a lens, an eye, something that's recording, it has a limit. And you've put together an excellent presentation. So what we're hoping to do with this presentation is raise up both sides of the debate, both globe earthers and flat earthers, to come together and actually look at this, because we're the virtual reality camp. And we're trying to show you guys, hey, look, neither of you can claim that the observation that you're making proves either one. Now, obviously, everything is observably flat, right? And we can use the way that the principles of water work, and, we can try spinning things and find how disastrous all these things are. But tonight, Jason, I'm excited for your presentation. We're going to get into these slides, and you've got some real world observations. Now, we're both, photographers. And I think that has a lot to do with, basically how we understand our vision works and then the limits that we have within these cameras that we use.
Yeah, the cameras, the 3D modeling programs, and then the state of tech where everything's at, understanding the resolution of the screen that you're watching something on, the resolution of the camera that's filming something, and what that all means. So there's a little bit of technical stuff mixed in here, but it's not going to be formulas that you need to know to get by every day. This is going to be stuff that you're going to see that there are 6 conditions, 6 things that if any one of these things fails, that's the limit of your circular sight. So we don't see too far. We see exactly as far as these conditions allow, and we got to get into detail showing everybody how these conditions affect everything that we see. And we've got lots of great video footage to show everybody. We've got the models out. We've got 3D models in motion. We've got SketchUp, whole bunch of things so that we can visually, graphically back up all the things that we're saying. We're not just blowing smoke out of our you-know-what. So with that, let's go ahead and talk about what these 6 conditions are. So we've got 6 conditions of resolving failure, where if any single one of these things failed, your image isn't resolvable. So we are going to be covering angular size. We've talked about this before. Angular resolution, we've covered that. Brightness, we haven't gotten into much detail before, but what a key factor when what we're talking about is light. How bright is it, and how quickly does that brightness fade away? Because without the light, you can't see it, right? Contrast, I think by the end of this podcast, everybody's going to start to realize just how important contrast is to being able to resolve something. We've all thought about this before, the environmental transmission things. This is fog, rain, smog, you name it, right? Like, how many can you list of environmental?
So many.
Yeah. And then 6, the ground overlapping sight ranges. So this is something that we've harped on a lot, how there's a distance to the horizon when perspectives put into play. We don't have orthographic view. We don't live in a 2D world. And as soon as you have a 3D world with perspective applied, there's a circle of sight that is based on your elevation. You can only see so far to the horizon based on your elevation. So we'll go over that again in detail. But to set the stage here, light itself is a very special feature within this world that's built on wavelength. How many times have you heard light referred to as a wavelength before? And what's your initial gut reaction to hearing that light's a wave?
Yeah, well, that it might propagate similar to the waves that we see in the ocean.
Sure. The way sound does. So all these different things, they are actually being transmitted as a wave. All right. So light has a wavelength to it, and that's actually what determines what color it is. Now, the longer wavelengths are the ones around red, orange, yellow, which also means that they're the first ones to be cut off, because the longer the wavelength is, when you narrow your field of view and you narrow your angular resolution, you literally cut off that light first. So when you see something disappearing in the distance, the reds, the yellows, those things disappear first, and it's the blues and the violets, those colors that have the shortest wavelength that are going to last the longest. All right, so you have wavelength that cuts things off. And what's it say here? Light's wave nature sets a limit before detail can be resolved. So when angular separation falls below the limit, separable details merges. We're going to be looking at all these examples of when an image starts to merge and become unresolvable anymore. You can't figure it out.
Yeah, it becomes a blur. You don't see the individual wave lines. You won't see, everything will just sort of blur out.
Yeah. So the first thing that plays a huge factor in whether or not you're going to be able to see it but I mean, all these factors are going to be dependent all at the same time. So angular size, if an object's apparent size large enough at that distance. So go out and test this for yourself, everybody. Look at something that's up close and walk away from it. And what happens? It shrinks. It shrinks. It gets smaller and smaller and smaller the farther you go away from it. And that is its measurement of its angular size. And so increasing distance means decreasing apparent angular size. If the object subtends, and I'm going to tell anybody what subtends refers to.
It's basically the distance or the area that an object will take up in your field of view.
Yeah, so whatever size the object is, if it's a car out at the horizon, if you measure from the front bumper to the back bumper, that angle that you get is the area that it subtends, the area that it occupies. Too little angular space, it approaches the limit of useful detection. Too small to actually even see what it is anymore. So angular size has to do with distance, but there's another factor that's closely related, and that is angular resolution. So can the eye separate the object or its details? So if you're looking at this, maybe Lighthouse right here, you can see in the zoom up all this separable detail being resolved. You can see, the shape of the window, the outline of the trims, even the different colored tiles right here. That right there is resolvable, right? And at a close distance, the whole building's resolvable. But with the distance, right, all those details begin to merge, and it just becomes a blur, where now all of a sudden you're just seeing outlines of things. You see the edges of the building, but the windows seem to have disappeared. You can't see that they're individual tiles, any of that kind of stuff. And it's just fuzzing out. So detail is lost when separable features merge below the eye's resolution limit. Mm-hmm. Eye has an angular resolution limit of 1 arc minute. And that's it. So once something gets smaller than 1 arc minute, poof, it's gone. We'll be looking at some of those examples and videos. Another huge factor that we need to be considering as we're going through all this footage is the brightness of something. And so great example of that would be like a lighthouse. And so there's a law, a programmed law in reality as far as how light diminishes. And it actually follows the it's not the square root, it's the
inverse square law.
Inverse square law. Thank you. Yeah. So with the inverse square law, you have something, if you have a set distance, let's call it 1 mile here, and we measure the illumination there, we'll call that 100% luminance right there. Now, if we go to 2 miles, right, double it, only a quarter of the light will be there, 25%. So as you double the distance, you get 1/4 of the received light. So at 4 miles, you only get a 16th. All right. So if you keep going here, you can see how rapidly light diminishes. So brightness falls rapidly with distance. Below the detection threshold, a light is not visible. Think about it. If you have somebody with a Bic lighter lit walking away from you, how far does the person go where you just can't see the light whatsoever anymore? And everybody's got the cell phones on walking around right now. And how far can you see it? Well, not that far, right? Because of the inverse square law being applied here. And, if you think about it a little bit deeper, the inverse square law, because you are doing math like taking the square roots of things, you can tell it's a calculation. It's not just something nature made up that, okay, I'm going to be a quarter the strength every time you double it, right? It's very, very formula driven.
Yeah, well, and it's, too matter of fact. It's too, the same as the sun, the moon, and the stars. It works too well. It's perfect, which we know anything that we create or anything that we observe in reality, that we try to make doesn't work perfectly. So you have to have an incredible designer.
Yeah. Contrast. This is one that, as we go through the examples, it's going to be really apparent the reason why we're not seeing so far. And it has to do with contrast, everybody. Does the surviving image differ enough from its background? How many times have you thought about the importance of differing from the background? Well, as distance increases, the optical path through the atmosphere grows longer. Scattered light adds background brightness and reduces object contrast. So the increasing optical path plus haze, reduce contrast exponentially. So low contrast equals lost detail. At the limit, the image merges with the background. So let's take a look at our example here. And there's an actual formula. So based on a distance, you can tell how much contrast is going to be lost. At 5 miles, you've got 89% of the contrast. At 10, you've got roughly 80%. At 25 miles, you're nearing half, 56% of your contrast. 50 miles, you've got 31% of the contrast. 75 miles, 17.5%. 100 miles, you're below 10% of the contrast. At 125 miles, we're at this 5.5%, which ChatGPT is saying is basically where things disappear. Once it goes less than this 5.5% contrast right here. So pay attention to this building right here. And when we start looking at some long distance footage, and you are going to see this over and over and over again, this contrast loss as we're trying to look at things at a far distance. So as contrast falls, detail fades and the image merges with the background. Unresolvable. Once it's merged with the background there, you can't see what anything is anymore.
So for me, basically, when I first ran up into this, before I knew exactly what was going on, I was driving all around Lake Ontario, trying to film the CN Tower from, 30, 40, as far away, miles away as I could get. And beyond 20 miles, it was really tough due to like smog, haze, like Jason's saying. So basically the CN Tower, because it's not even a wide building, it's just a small tower, it would blend into the blue sky in the background. Now 20, 30 miles, you can clearly see it, including Toronto's in a bowl, so it's lower, all the surrounding areas. You have great vantage points because they're higher in elevation. But this is something that's very easy to go out and understand. It's not being discussed in the community between the debates of is the earth flat or is it round, or what type of a reality are we in? But it is important that everybody understands how much of a role contrast plays. We all know contrast when we're, tuning our televisions or our screens and we want crisper, you can see details better with the higher contrast that you have. And it's important that we take into consideration how this works, and that we start to understand that how the distance to the vision. So after 5.5% of the contrast of anything that you're trying to view, it's gone. Can't see it anymore.
Yeah. And this happens at 125 miles. So we're going to be showing everybody tonight how the world record that we showed before, Mount Everest from 125 miles, that's as far as a record you're ever going to get, because we're at this contrast threshold where if you go further and further and further, there's going to be less and less contrast. And even though Everest would be above the horizon and it's a clear day, you're looking at it, there just won't be enough contrast there to actually distinguish that you're looking at it.
And keep in mind, when looking for something to observe from the furthest distance away, you want to have something that has the highest elevation point and the largest type of a structure. That's why we're even able to see the peak of Everest from the distance of Kathmandu. Any other types of observations, you can't even begin to get close to it. Now, I know the Rocky Mountains in the West Coast, you can see from 30 miles away, but not much more, right? And you at home, you can do these types of tests. You can find buildings, you can look for observation points that are farther and farther distances away, and you can start to observe this phenomenon, these settings of the reality that we're in for yourself.
Absolutely. So that's the fourth condition that needs to be met when you're viewing something. Now, here's our fifth condition.
So this is the
and
one you
that's-
hear about from all the, David Weiss and all the flat earthers, Mark, Eric. Whenever somebody says, well, why can't we see, the Eiffel Tower from New York, right? And people, it's ridiculous, but this is the common answer: fog, haze, rain, snow, ice, clouds, smoke, dust, sand, pollution, aerosols, long air paths, or heat shimmer turbulence above the different observation sites. These are the interesting things that we do have to take into account. Some of these are treacherous. Fog being the absolute worst.
Quarter mile visibility, right?
Less 100 feet. I mean, I've been in some I had to pull over. I couldn't even drive due to some of the depth and thickness of fogs that I've actually experienced.
Can't see your feet anymore.
It's crazy what takes place.
So this is a nice graphic. It shows that these right here are scattering effects. So we have the light trying to travel a path, and these things right here are going to scatter the light, and it's going to just reflect it off in a bunch of different directions. Then you have different things that absorb the light. So the dust, sand, that kind of stuff in there, it's not scattering it, it's just sucking up the light and keeping those light particles from traveling through. Then in that long air path, you have the heat shimmer, turbulence, stuff like that. We're going to be looking at a lot of footage that as you zoom in at a very long distance, you're going to see this jello effect as well. And it's a combination of all these things right here compiling on each other. So any one of these things is only going to shorten the distance that you can see. None of these things amplify it.
Yes.
And make you be able to see farther, right?
Yeah, you'll get the whole refraction crew coming in. So the AE mappers, because the sun and moon and all the luminaries completely circle off of their model of, one single pole person pizza dome reality. They say, oh, it's refraction. And then the globers say, oh, you can only see that because it's refraction, or that works because of refraction. So the two of them like to misuse actual observable evidence.
Absolutely. All right. So our sixth condition, something that's essential for something to be able to see, is that the elevations, the ground plus the overlapping sight ranges. And this is something we've talked about for a long, long time now. At first, you have to have no obstructions in the way. If you're trying to see this building right here, but there's a tree in front of it, all right, obviously the obstruction is going to block you from being able to see this building. If there's a parking garage right here, you're going to be blocked by the parking garage, and you're going to not be able to see that portion. So it has to be above ground, and it has to be unobstructed by anything else in order for it to be seen by you in your circle of sight, right?
Yeah, it has to be within your observable circle of sight, and then it has to have the right elevation to meet conditions. And then the further and further you travel away, the less and less of the object you'll see due to these actual circumstances.
Yeah, so this is one of the formulas that we've talked about. The distance to the horizon on a plane is the square root of the height of the observer times 1.22459, and that'll give you a distance to the horizon in miles. Now, it is essential that your circle of sight and the circle of sight of whatever object that you're trying to view are intersecting. All right, so let's go through this graphic a little bit, point this out to people that you've got observer over here on this tower. He's got an eye height right here, and there's this tower out in the distance that's at this height over here. Now, using the formula, you can calculate the distance between the two, and those those two circles must overlap. So this observer right here, if he has this size circle, this observer has this size circle, observer A cannot see observer B. Does that make sense to you?
Absolutely. But both observer A and B can see the light that would be in the mutual space.
Yeah. So if you have a person standing here at D, observer A can see him, observer B can see him. The observer at D can probably see both A and B.
Looking different directions, 180.
But A cannot see B, and this is all on a flat plane. This has nothing to do with curvature. Formula's simply giving you a distance to the horizon. And so this observer, these circles have to meet in order for the two to be able to see each other. If not, they won't. It's that simple.
Well, and the distance, the mathematical part that you don't completely need to, get too deep into, but the 1.22459, that's the actual distance that was used to back engineer the spherical globular ball Earth model. This is what they used for the radius, right? The R.
Yes. So if there is no line of sight, there is no image to resolve. It's that simple. It's that important. The circles of sight, the distance to the horizon based on the elevation of the observer and the object that you're attempting to observe. All right. Let's go ahead and take a break right there.
Okay.
And then we will come back and we'll get into some of the evidence and showing models and all that fun stuff. How's that sound?
Let's go.
Cuckoo kiss, cuckoo, you cuckoo kiss, you cuckoo kiss, cuckoo, you cuckoo kiss, cuckoo, we were cuckoo kiss. Your cold kiss cut across my lips.
And we are back. And we are starting off with the Andrew Marsh that we've been using for so long that shows the path of the luminaries around an observer on a fixed and stationary plane. Just want to show everybody real quickly here that this is the way we actually go out and measure these things. If you put a surveyor down here at the center of this and he sets up his theodolite and he's pointing it at the sun all day long, he is going to get these azimuth and altitude readings. And yeah, it actually does show the luminaries going down and around underneath. Let's go ahead and let it make a full loop right here. But yeah, so all the measurements come, they level up their total station, whatever it is that they're using, and they get these elevation angles and azimuths off of a flat plane. And I bring this up because what the Globers have done is they've taken this information right here and they have stuck it onto the side of a spinning space ball, right? All right, so now what they do is if you change your latitude, they change it like this, where they keep all these it's not rotating. All right. So if you look at it from the side here and you use the latitude, you can see them. They always keep it pointed up like this. Their baseline's changing, and then it's going around. All right, but all these measurements came from this model right here on a flat plane.
Flat and motionless plane, and then they move it, and then they switch it from the celestial movement to the earthly one.
Yeah, so I want to show you. Let's start with this one here. So if you put this out here where you've got all these circles of sight, right? So each one of these, you're supposed to visualize a person in here. This is their circle of sight as far as they can see. The Globers have pointed it all out towards these are all make parallel lines. But we've talked about how if you set up your circle of sight here, what they like to say is that the baseline is constantly changing. The baseline just changes, right? So it's not a baseline, it's a circle in their world. The baseline just changes every which way you go. In a real world, what you would have to do is if I'm here at the equator and Ron's up at 10 degrees north latitude, and we both want to take a measurement of the sun at the same time. So if we both level out our theodolites, surveying equipment, whatever it is, and I take a reading and it's 90 degrees overhead, and Ron leveled his up over here, and he takes a reading and it's at 80 degrees right here. I got to say, whoa, just a second, Ron, you didn't change your baseline, right? Because your baseline is 10 degrees different than my baseline. So whatever measurement you get, go ahead and subtract that amount from my baseline. That's the whole purpose of having a baseline. So what the Globers do is they take what's happening in the circle of sight, they put it all the way around here, have the baseline change a full 180 degrees, where from here down to here, it's 180 degrees changed. They've never adjusted their baseline once. And that is how they built the globe, right? So once you understand that trick, it's over. You've busted their whole psyop. They changed the baseline, right? They say, well, it's because it's a ball. No, you didn't change the baseline, which means it's a plane. Right?
That's right.
If you take this and you adjust the latitude here,
There you go.
see the plane never changed.
That's right.
The
North, east, south, and west always become directions in your azimuth, right? And the elevation to the luminary is what changes here. As you move around on Earth in this realm, the Earth will always remain and be measured flat, and the path that the stars take around you will always tilt based on your latitude. And that's exactly what they took and back engineered and created their fantasy sphere.
Well, so the reason why I bring this up is because in the globe, everybody thinks that in this circle of sight right here, that as long as the ground is not obstructing your view, that you can see trillions, quadrillions, quintillions of miles away. They really do believe that you can just look out and around you and see thousands of light years.
It's crazy
away from you.
Yeah, it's crazy. And you can get deep into the whole, Halton ARP and, the quasar problem when they had the redshift with the local quasars, they said. Everything's local, right? Everything
Yep.
is much closer than what we've been taught. It's a small world. That song, I'm not the best singer. I'm a little better on guitar or bass. But we start to understand that the realm was created and it's this size and it's basically like a coop. We're not able to escape it. And if you raise animals and there's predators, you'll start to understand the reasons why it is the way that it is for now. But one thing is for sure, Jason, when these globe Earth guys take their measurements, they always measure off of a flat stationary plane. There's never an adjustment for latitude or longitude. The only thing that happens is the angle in the sky to the observation changes, not the ground.
Absolutely. So we bring this up. This is one of the three options that we're going through tonight. This is spaceballers. The reason why they think they can see trillions of miles away. And it's because they think that the only thing that stops vision is the ground. Otherwise, other than that, it's just a free for all.
The curve.
You can see for infinity, right?
The curve. They say you can only see to the edge of the curve on Earth. But then in the sky, NASA, what is it? The Jesuits that invented the mega giant telescope. What is it called? Satan, right? Lucifer. And they're purporting to measure, trillions, like to the edge of the known universe due to the color of red that they see in the light in the sky. And it's not even fathomable, the numbers that they're saying. And then when you show us, Jason, just how far we can see a candle from, right? And then you'd have to think, well, if something is on the outer reaches of the universe, if we were to reverse the inverse square law with the brightness of the light, how big are these luminaries on the outer edges of the universe? Would they be like
quintillions of miles wide?
Larger than the sun? Would it be a sun times a trillion or, a quadrillion? How large would these things be? And this is the thing with all of major science, with all of the heliocentrism, Big Bang cosmology, evolution theories, they have these, just model killers. Jason, you stumbled upon yet another one, the distance that we can see. And let's be, grown-ups here. Let's put on our thinking hats and work together to actually see the observable truth, the evidence. Just like when we watch a sunrise or sunset, you literally see the sun come up out of the ground, right? Rise up through clouds with clouds in front of it, behind it, rise up over your head, and then set down through more clouds. It'll drop right down through clouds, clearly right illuminating just those little clouds on your horizon, and then set and sink straight into the ground.
If you're at water, you'll see the little hot spot and you'll see the sun merge with the water.
The green flash. There's so many things you'll see, and you start to understand that this is a supernatural realm, that the motions in the heavenly bodies were created in a way to interact with us, kind of like having the glasses on. Our eyes and our spirits are tuned to the virtual reality where we get basically our own personal view of the sky. It's incredible. You just have to open up your eyes and see it. It's crazy. So, Jason, before you move on to the next slide information or video, I happened to glance up and I caught the moon, and the moon is roughly half. And so if we were living like we should be and following the sky and the signs, the sun, the moon, and the stars, I would know that we are a quarter of the way through a month, right? As soon as that half moon becomes full, I know I am halfway through a month, right? Nobody in the Gregorian calendar that follows the mainstream science could ever live according to the sun, the seasons, and the stars. But we do. And it's just basic, simple things that I wish I could share with everybody in the realm.
Well, based on where the moon is right now, can you guess what day of the month it is on the true Hebrew calendar?
Tell us, Jason. I have a good understanding of what day it is. Not the 8th day, but it is the
9th of Av.
The
at
true.
at the true 9th of Av at sundown. And yeah. So that's part of being able to tell time with the luminaries. Absolutely what
Right.
you were talking about. Let's go on to what the fake flat earthers have to say about how far we can see. So we have the globers that think that they can see quintillions of miles, thousands of light years away, and the original personal atmospheric domer, guess who it was?
Jeranism.
Jeranism. He made up the personal atmospheric dome, and that has been the going phrase ever since. And yeah, let's hear what Jaron had to say about personal atmospheric dome. And this is from Godless Engineer. How come all the
Didn't he moderate our
spinning-
debate? Like,
he did.
I
All the spinning space followers got to be atheists, right?
I think I put him in the video with the dunce cap on.
Yep. So here's Jaron. Play.
Atmospheric dome. It is not getting closer to the horizon. We know that, but everything we see happens in our personal little dome. Now we can see the sun. As the sun goes away from us, now we understand why the
Look at these graphics that Jaron produced. sun over here, but sun over here, but here, but here. That's the absolute most confusing, asinine shit ever.
I mean, Jaron was right from day one. Ladies and gentlemen, if you're interested, if you go to Beyond Flat Earth, which is linked all over our channels, if you go to Jason's homepage, my homepage, Whitey's homepage, you'll find on there a debate from me with Jaron on, it was a conversation on September 11th, 2016, where he comes up with the most asinine, clown, nonsensical things. We called him on it for a decade. And we said you were going to be the one to flip. We said you were just trying to prove that the earth was a globe all along. We were the only ones. Everybody hated us for it. Here we are going over that same information again. If you go, it's called Up the Wall with Jeranism. And you will absolutely see, I was explaining to him so much of this stuff, and Godless Engineer, their whole, Steve McRae, what is that group that they had, Red's Rhetoric, who won't debate you anymore, Jason. They won't. Craig won't. Mucktoon won't debate us. What happened to these guys?
Yeah, their whole debate channel fell apart. It was just, that's what happens when you have godless, godless engineers.
The two guys, Kyle and Steve, started to fight over funds, right? They started to screw each other over, just like everybody does. Like, if people were just interested in what's going on, the truth and stuff like that. So Jaron was the one who brought up the personal atmospheric dome nonsense. And when he did that, he was trying to justify false observations to support the pressurized AE Freemason New World Order map model, where they have the one sun circling around a one pole Earth. Right. This was the setup, the big setup. And what they tried to do with characters like Rob Skiba, Zen Garcia, and many others was then to tie this map, this model, literally to the Bible. And then when Jaron debunked this map and model by going to Antarctica and proving that there is a second pole, they were going to say that the Bible was also not true.
That was the plan. We were able to sniff it out. Here he goes on with his personal atmospheric dome.
happens above us displays for us in our own personal atmospheric dome.
You know what this reminds me of? You know in Destiny 2 that
So this personal atmospheric dome, all it does is set it up for a guy like Godless Engineer to come in and be able to mock, right?
Yeah.
Because there's no dome around you.
It's ridiculous.
Here's another one.
is within the person's own personal dome, along with the stars and a miniature plane. Yeah, the plane that's smaller than the person. I don't know how the plane is smaller than the person. The person looks like Jiminy Cricket.
So he's just mocking.
Stars, too, are included in your atmospheric dome.
In your own personal atmospheric dome. Everybody has a dome that protects them from all the science that's gonna hurt them.
Now, if a plane flies over your head in Boston, someone in Florida can't see it. It's too far. Same goes for Polaris from further than the equator.
Oh, what the fuck
Here we've
is
got
this?
another drawing. It's labeled a few places. We'll look at label.
Look at this garbage.
It's really bad.
You've got the sun over here, but it's up here
Actually, there.
going that way.
That's the real sun. And then that other one, E, is the observable sun. And then what Jaron does is he gets a magnifying dome and then a flashlight, and then he shines it here and says, "Look over here. You see the reflection? That's the fake sun. This is the real sun."
Yeah, so that was just a crude drawing of the Walter Bislin model, where what we have here is what the personal atmospheric dome they've got down here, and then they've got what's supposed to be the real luminaries up here rotating like this. So if you move it like this, you can see. All right, so here's the moon with the gray line here. It's up here, but they actually show it. Okay, it's actually rising right here. Then you have your sun coming around, and the sun's supposed to be up here, but it's actually
Down there.
rising right here, right? And so this right here is the personal atmospheric dome that David Weiss and all these guys have shared, saying, "Oh, see, this fixes it."
Yeah. Jake
This
the
fixes-
asshole. He was the one that said he literally fixed it with this. Now, what this shows is that with a Cartesian grid system, right, you can map spherical objects like a celestial sphere that you just make up that's imaginary. You can wrap that through a Cartesian system and you can put it over any shape, any model, and you can line it up. But does it match what we witness in reality? And the answer is no. The Earth, right, has two poles. You
Mhm.
can't have a south pole that's the entirety of the outside of your model of reality, because you actually do away with things like navigation. You can't navigate anymore. Sure, maybe if everyone could see Polaris, you might be able to make it work, but east and west and north and south become very, very paradoxical in this nonsensical reality. And that's why they go with it. What it is the squished globe. You're only getting half of it, right? So you'd literally need to put the other half. You really need to have the AE map extend out to the equator, and then from the equator to the outside of the map, you need to put on the underside of this model and have it truncate into a point as well.
We're going to show you from a few different things, but if you take a look here, look at what we have here. We have the South Pole coming up. So at the equator, we've got the North Pole and the South Pole on the horizon. If you go north of the equator, here's the North Pole rising. But if you go south of the equator, you have the South Pole rising. And then just the absurdity here, they have the luminaries doing circles up here. And you can see that now all of a sudden, this sun right here is supposed to be rising right here and following this path right here in that personal atmospheric dome, going around like this. And as the sun is now up here, it's going to be rotating out this direction in the personal atmospheric dome. It's coming down and setting
It's going the other way.
to the southwest.
That was the problem that I had with Jaron. Was trying to explain to him that, hey man, your circling sun going the one direction all the time doesn't work. In reality, the sun goes one direction in the north and then the other direction in the south. And you need to have two poles to describe the reality that we're in. You know, it's not that it's complicated. It's that we have to unlearn the things that we've been taught, all the disinformation, and we have to start to understand how it could actually work here in this reality. And so, you know, there was many other people that tried to use this model. Who was it? Stephen
Alonzo.
Alonzo, he was saying that the flat Earth predicted this, the observation of having a sun up all day in Antarctica. And he used this as his model. Sadly, this doesn't do it. And just for everybody that's tuning in, do you have the moleweed, uh, our Earth, what we actually use to show people? Doesn't matter which projection you use. Anybody can use any projection. That's the Onion 2D, and now I need the one that we can actually manipulate. It's on the website.
Yeah, I just want to show everybody this one quick. This is Earth's lat and longitude coordinate system to scale. This is a literally to scale version of it. So this has got the 60 nautical miles per degree at the equator, 59 nautical miles per degree at 10 degrees north, 10 degrees south, and then progressively it gets smaller and smaller and smaller until you get to the North Pole and the South Pole, where it's a point. It has no length whatsoever. So this is a to scale representation. But it, what you were asking for, it looks very similar to the moleweed, where
Yeah, but that's not the interactable program. So the problem that I'm trying to articulate here is that to have an area of reality that you're in accurate, you have to have the map of the world selected on your area, right? Nothing exists completely perfectly on any projection than the way that it actually takes place in reality. So here we go. Now you're getting to the correct
moleweed.
moleweed. This is the right way. So only the center longitude and latitude lines where they meet there are accurate. Everything else is distorted in reality. Forget whether the earth ground is curved, right? Look at the way that the latitude and longitude lines work, how it's a grid Cartesian system, and how the only way you can have a true square, right? Because we calculate, move, and build things in square measurements, right? 3, 4, 5, and so on. You can double, triple, and quadruple those numbers to build squares. You can see that moving left and right, up and down, you get slightly imperfect squares. And the only way to keep those absolutely 100% perfectly true is to have it always locked in on one position. So you will never be able to have a better map than this one, because this one gives you the limitless amounts of positions that you can put the map in. So this is the end of all debates on which map works. This is a map that works on all models. It works for every idea, whether it be a flat earth or a sphere. And which do we actually comport with when we go out and observe and interact with reality, is that the earth is flat. And here we have, go ahead.
The reason why this works is it's stereographic. It has two poles, because Earth has a North Pole and a South Pole. This is the way to render it. So if you do, we always had this version of it like this. This is the way it began.
There it is.
And so if you're centered to France, right here, you get the map that we were sharing before that was static. We couldn't move it around. But now we know that if you wanted to have a map of the Mexico area, you click there, and now you can see that the grid lines are actually all drawn to scale now, because the latitude gets shorter as you go farther north, as we were showing with the 2D version of this. The latitudes get shorter as you go to the north and to the south.
Right. This is there's a blending that takes place, right? You have to always be locally measuring, and then there are these other charts that we can measure off of, so that we can always have the correct angles and the spaces that were needed to move where we need to go. This is how people actually navigate. They chart courses through these squares. They don't zoom out. No one has a sphere in their cockpit. You know, the only people that like stupid apps for like Wolfie 6020 they use, it's just nonsensical. But this is the way that, and this is the most advanced, you know, theory, understanding the most advanced virtual reality, why it was built this way, the limitless possibilities of our reality, instead of it being a easily identifiable cage with a single, you know, pole up at the top here, like the AE map and model. People, if the Earth was like this, you would literally see the sun pop into view up in the sky, circle around you, right? Then you'd see it disappear up in the sky again, right? Everybody would know there's Polaris. There would be no south stars. There would be no other southern constellation, the crux that spins the other direction, right? But when you understand that the circle of sight that we have here mixed in with the map that Jason has below, you start to get the actual true understanding of how it works. You got stellarium. Did you have other observations that you wanted to bring up? I know you also have, we could probably do a song break. I know you've got the observations with, zoom photography so that we can see, degradations and things like that.
Yeah, one more thing to get through. So we had Jaron that brought out the personal atmospheric dome. And then we had guys like Jake come along and use it for the longest time. But we've bent him to our will, where he is now being forced to language it more and more correct. So let's hear how Jake has changed his tune and hear what he's saying here.
Projected within your own virtual dome. Everything works perfect. And it doesn't matter if you're using a AE map or a Mercator map or whatever. I can't tell you exactly how the land masses are all laid out and positioned for sure.
We can.
But what I can tell you is if you use the correct sunrise and sunset data, which is observed and it's cataloged, that you can at least get that part right. So what I did is I did away with the one circling sun and the one circling moon, which is provably wrong. And instead, I localized your sunrise and sunset, because we see it rise and set most of the time, and made all of that local within each of our own personal domes. And so I believe this is more of like a virtual realm that we live in. And so programs like Stellarium, which will show you where the stars are positioned for you in any given area, or programs like SunCalc, which will show you where the sunrise and sunset angles are going to be. They're basically showing you that the sun is going to rise in those areas from those angles, which it defies all the models we've been given. So if you really look into the
nice try.
No, nice try. Yeah. So he is saying virtual dome now. He's not just saying atmospheric dome, right? And he's given way to virtual reality, but he still does everything he can to mislead people into what this personal localized light source thing is. He brought up Stellarium. We're going to be getting into that. Let's go ahead and take a break before we start showing people how this really works. How's that sound?
Let's go.
Only wanna be here
Well, the song wasn't long enough to play the footage, but don't worry, we got it. Yeah, we're going to take a look at what the longest recorded actual observation from ground is. And we started talking about this on January 6th of 2024. This was the real insurrection day right here.
Yeah.
When we started showing people just how far you can see. So let's check this out.
That's what's given him the opportunity to see.
Do a little jump.
Here we go.
We're just going to take the guy's word for it. 200 kilometers comes out to like 125 miles, which is 20 miles longer than the previous record where we could see Mount Rainier from a location at 105 miles. So let's check this out.
All right, hold on. Can you see where Mount Everest is yet?
Barely.
It's not this one.
No, it's just resolvable to the right.
Yeah, it's not this one.
No.
It's not this one.
No.
It's
There it
this
is.
one.
We're actually looking at this peak back here. So you can see through this notch.
All right, it's clearest. You got it to focus.
They're back behind.
Right there.
There's Mount Everest.
Yeah, so seeing through this notch, and what is it that is taking place here, everybody? See if anybody's gonna pass the pop quiz. It's not ground occlusion, right?
No.
It's not being blocked by anything on the ground. What is happening here? This is contrast extinction. So based on the distance here, 125 miles, we're down to the 5.5% contrast that's left. And you can see that the mountain is going to be blurring with the background.
Everest back there. All right, so boom. That is your world record holder. Anybody that says anything else more than 200 kilometers or 125 miles, they got to back it up with some real evidence. Jaren's example of Kenegu, absolutely fake. All those Beyond Horizons pictures, absolutely fake. So much fake evidence has been created for a flat earth that's not necessary, because all the evidence proves that it's flat. You don't need to use CGI.
Yeah, just someone with a camera. They don't even have to know what they're doing. This person didn't know they were filming the longest observable record for an observation on Earth. They didn't know.
Look at how close the contrast is becoming here. So just a little bit more distance, and contrast alone will have shut it off. It's got the height, it's got the angular size to be able to be seen, but it's still, if you go a little bit further away, contrast alone is going to make it unrecognizable. It won't show up. It'll just look like it's sky.
Yeah.
I got some roosters and chickens in the shot too.
Yeah, look at this. So he actually got, he's getting in there.
And of course, it's with the flat earther's choice of camera, the Nikon P1000, that sets the record.
This guy got it. That's quite a shot there.
They just a back up here so you can see just how far away that actually is. Keep going, keep going. There.
No infrared needed.
Then a little bit of a pan around so you can see the whole area around there. But that right there
Get
is
a mute on that.
What's that?
No, continue. Just mute it if you're going to keep playing it.
Yeah, no, that's good. I want to show you some other examples. These are not flat earth videos, everybody. These are just people that are amazed by the amount of zoom that the P1000 and now the P1100 have. But here's some examples, and this one's a relatively close example, and I'm using this where you can still see, all right, there's a logo on this backpack. There's this person's got some red on the side of their head. This one does too over here. You can tell that, you know, this person's got a hat. We're at, I think this was, see if it says, this is 3.5 miles, 3.5. We don't need all the volume. Then he shows some other stuff and different distances. This one right here. So he starts back here. You got the mountain. You see that far, that distance. All right, so that was the end of the optical zoom right there. This is like 8 miles away. And now could you tell if somebody's wearing a hat up here? What if they had some red on the side of their head?
Really can't tell.
No, you can't tell at all. You can't tell if it's a man, a woman, if they're wearing backpacks. Even this is digital zoom now, so this is just the optics aren't increasing it now. This is crop zooming, so the image gets a little bit bigger, but it actually becomes more blurry as you do so. So at 8 miles, you get this gelatin, right? You would not be able to figure out who was who at 8 miles. We've got some other examples. Let's get, these are just the ordinary things that you can do yourself, everybody. This is less than 7 miles. We don't need that. Here's 12.12 miles. So we saw the 8 mile example. Let's take a look at, this is the closest. This one gets at 12.12 miles. And here we have a nice brightly lit mountain. And so you can actually even see a little bit of color here. You can see that there is red over here, but there's no way of being able to distinguish a person, male, female. See this gelatin?
The waves.
So even though we have the contrast, we still have an atmospheric effect that's creating that gelatin waviness when you're out at a distance like this. So that's the 12.2. Let's go on to this one right here. This one we can break down a little bit. This guy did a great job of pointing out where he's filming from, what he's filming to, and the elevations of those things. And it's not like a flat earth video whatsoever. It's super zoom. It's somebody out here.
Zoomer
P1000. So he shows his location. And he shows path of this island, this coast over here. He's pointing these things out. Then he's going to extend his line all the way out to what it is that he says he's recording. You can see his kilometers going up. We're at 49, 50, 60, 70, 80. We're up to 91, 90, 92 kilometers, 93 kilometers.
That's pretty far. 57 miles.
57 miles. So what's he going to get here? Well, let's let him show us. Begin the zoom. So he's coming in. And he's going to point out the things that he pointed out on the map. All right, so here's the Brown Island. This is 8 kilometers. This one's 16 kilometers. This one is 25 kilometers. I must do a pause right here and prep you for when he unhighlights these things. I want to point something out to y'all. All right. So right here, you can clearly see that in the foreground, we have the greenness of the grass. We have just a totally different type of color scheme here than this island out here, and this island here. All right, so these have lost contrast to the point where, let's go ahead and bring up our...
Yeah, the islands are still on the shoreline, assuming those aren't clouds, that they're even whiter, less contrast on another set of islands there that he's going to zoom into.
Yeah, so this is the whole contrast thing we're talking about. The 5, 10, 25. Look at the difference at the 10 miles to the 25 miles. That's like 25% loss right there. And it just keeps falling off dramatically here. We have an example where we're going out to 57 miles here.
And it matches.
And so look at the contrast difference on these islands, that haze. How many times have you been driving in hilly area and you can see that you've got the green mountains near you, and then you've got the hazy mountains out at that 5, 10, 15 mile range? This is all contrast loss right here. And guess what? Here comes the island that he was talking about that's 57 miles away. And there's your peak of it.
It's a great observation.
But this is all we get. All right, this is the mountain. This is all the detail has been completely lost, and the mountain has almost completely merged with the background.
That's your 5.5.5%.
That's it right there. That is it right there. So at 57 miles, right? It doesn't matter. This could be a mountain that's 10 times the height. All right. You just put it back another 20 miles, 50 miles, and you're still not going to see it.
That's right. Instead of someone saying, well, if the earth was flat, we would be able to see those mountains in that range. And what we're showing is that, due to the loss of contrast, no, you just can't see it.
Just can't see it. So this is a great one. I've got a slide I can show regarding this. So this whole, we can see too far. They're harping on the fact that with curvature, too much of that mountain is being seen, as that should be
Earth is flat. They're right.
Yeah. But you're actually not seeing too far. We're showing you the evidence that 57 miles is really the cap, where if it was any further away, just due to contrast alone, it wouldn't be resolved. So the Mount Wellington to Mount Hobson, Mount Wellington, the observer is at 135 meters. That's 443 feet. That circle of sight is 41.5 kilometers or 25.8 statute miles. Mount Hobson, with a height of 627 meters, that's 2,057 feet. Circle of sight, 89.4 kilometers, 55.6 statute miles. As we were going before, those circles of sight must intersect, and they do.
They do.
All right, so,
oh, wow.
When you do
on a flat plane.
Yeah, when you do the distance to the horizon calculation for both of those, with those circles of sight, you have an intersection of roughly these miles right here. All right. So the combined mutual range, they could theoretically be seen from a distance of 81.4 statute miles, but we're already seeing the contrast extinction is letting us know you would never see it that far.
That's right.
Yeah. So the contrast loss at 57 statute miles, 73.4% of the contrast has been lost at 57 miles. Only 26.6% surviving. So do the circles of sight overlap? Yes, right? But you still could end up not being able to see it.
That's correct. Loss of contrast. And then conditions. We've gone through the 6 slides. We'll go back to them.
All right, so we've got another one. This one's got a multitude of examples. This is the P1100 they have out now. It's basically the same as the P1000, just a little bit of upgrades they gave it. So he gives, some long distance. This one's, like a 55 kilometer range. That's Mount Everest, just from a different view, a much closer view right there. We've got some of these I want to show just because you can clearly see the different contrast extinctions. So where you can see here, you're getting the greens, but then out at this ridge line over here, that's farther milked out. And then the one beyond that
looks smoked out.
Absolutely. Contrast extinction. Now, you brought up airplanes. So back in the day, we used to do things like film the chemtrail planes and see how far we could track them.
Yeah.
Have you ever noticed that these planes that are flying up here 35, 40,000 feet, when they fly overhead, that they literally come into view up here above the horizon and go out of view up here above the horizon?
It's something for the viewer to, take into consideration that you're not seeing the plane ever reach the horizon.
Yeah, look at these areas like this. You have the high contrast area. It's visible here, but you can hardly even tell if you were just looking. If you're just looking here,
can't see
it.
It's like a fog.
So if it wasn't for the white tops up here, you wouldn't even know the mountains were there. So flying things, you got little things. Obviously, as these things fly away, they disappear above the horizon. It's small. It's got an angular size. And even though it's got good contrast right here, it's just going to get small enough that it turns into a speck. And then its angular size plus your angular resolution, it's going to disappear. Even though no curvature is involved, this could be a perfectly clear day, great atmosphere, all that kind of stuff, and they're just going to shrink and disappear in the sky.
Every drone operator has experienced it, watching their drone go up or fly away. Every single one.
Yeah. What do we got? Here's a nice high contrast shot. Those are, you're going to be able to see the longest. But here you can see this foreground mountain. This one has contrast where you can see the green and you can sort of see the outlines of trees. Then you just go another distance farther and the contrast is lost here and you wouldn't be able to make out any trees in this area. And the mountain's losing its contrast, but you're still close enough.
It's lit up. It's a great shot. Other foreground images here are in cloud, but yet the mountain is not.
So here's another great example. What's the biggest thing that we can put up into the sky that we should be able to see forever if we're like globers, where you can see trillions of light years,
to the edge of the universe, right?
Yeah, no ground obstructing this. Massive size. You can have this be super bright colors, yet you know what happens with all these hot air balloons?
They disappear.
Yeah, they just get too small in angular size.
Contrast gets too low. They blend in with the background.
And they'll disappear.
So why can't, Michio Kaku or Neil deGrasse Tyson explain to us how they think they can see to the outer reaches of the universe? And we're showing them literal observations, and you can't see past 20, 30, 40, 50 miles, depending on the size of the object you're actually viewing.
So let's talk about that personal atmospheric dome for a second. And I want to show you a view in Stellarium that you probably haven't seen before. But this is an orthographic view. And so what we're saying is every single person on Earth has a circle of sight like this around them. And it moves like this. If you rotate it, so, bring the sun back up. Here we got the sun in Leo. Sun's going down, the sky's rotating. This is happening around each and every person in their circle of sight. But the atmosphere is not distorting things. Every single star in here is a pinpoint of light, and they're rotating in this exact same pattern. They never change their separation, their distance from each other.
Always perfect.
So there's no distortion. This is the path of the luminaries around the observer right there. Right? So as people understand this, when you're in the north, you can see that we have everything rotating around North Pole star right here. And then if I turn around to the south side, you're not seeing it, but if I take off the ground right here, you're going to see that there is the South Pole star. And this is right here in your circle of sight, everybody. So if I rotate this, if you're a person in the center of this, luminaries are rotating around you like this. Now, if I put the ground back on, this is the part that's above the ground. This is what you see, the stars rotating around you. And so this right here, we would call a God view. This is an unachievable view within the Earth reality. We all see it.
So hold on.
Yeah.
Before you leave. Okay. You can go back to it. Go ahead. Switch.
Yeah. This right here is the view that we all actually experience.
So
I've got it a little inflated here so that you can see.
So this is in the VR, in life, creation. You're within the VR. This is what you look around and see. You don't need Google glasses. It's your eyes, right? Your eyes, everyone's eyes. And we can look around and see this. Now, if you can go back to you called it God mode.
God mode.
So again, we're now going to have another plane of existence outside of this one, so we can look back in on what the observer sees. And what we find is an observer on a flat fixed plane. The sun, the moon, and the luminaries do exactly what it said in the book of Enoch and the Bible. This was exactly the way Enoch described it. There's 6 gates on the east, 6 gates on the west. The sun, the moon, and all the stars rise up out of those spaces on the east and the west, go above the observer, set, go under the ground, and then re-rise again every single day of all of creation since day one. This is what we can observe. It's perfect. It has the 12 different houses. So many mansions, Christ said, that his Father hath created. So there's 12 mansions in the sky, and those are regions or gates that the sun, the moon, and the stars, the wandering ones, travel through. If you tune in Sunday night, we're going to go over, the most ancient sort of Hebrew, names and what the actual 12 houses of the sky are. It'll be very interesting. That's just a sneak peek. Make sure you're tuned in for that. But what you definitely have is in those books, they talk about how the heavens are spherical, right? The moon, the sun, and the way that they warp or work around us is a spherical, and it's bridged with what Enoch teaches is like where we are, the ground, our circle of sight, the observations that we have, we can trace this azimuth, this circle around us, and then you can then mark out on the east and the west of this circle that we're looking at, you have the gates. And this is exactly what was taught, 5,000 years ago. And it's exactly, Jason has it on the diagram here. If you want to take over explaining it, you've got us looking north and east. West is directly behind Jason. So he would be looking towards sunrise, and it looks like the sun is setting from behind Jason. I can make that observation by just looking at what I see in the image.
Yeah, so this is another one of those God views, never ever attainable within Earth. We always see it from the first person's perspective in the center of this, seeing this rotate around us like stellarium, like this, right? It's rotating around us.
I hope everybody's understanding these illustrations, these graphics, bridging these two things, the heavenly understanding with the earthly is quite complicated, Jason, but I do hope that the viewers that are tuning in are starting to understand and see how this is working.
Yeah, so we do have atmospheric limits. We do have brightness limits. We do have ground limits. We have the 6 things that we listed all within our personal circle of sight, the distance that we can see to the horizon, and we all see the luminaries rotating around us like we keep showing with stellarium. Let's go back into the first person view once again. So we're inside here. Let's get that sun up above the ground. Now we can see some light.
You can notice that the S on the left, if we were on a sphere, everybody, that S would be below our feet. You can't have south be a direction outwards and also be below your feet.
Yeah, it's a horizontal plane circle, your circle of sight. Use that term. It's real. So it's not a personal atmospheric dome. These grid lines are not it's not a dome that the lights are reflecting on, but it is hemispherical.
The nature of the way the luminaries wrap around you is hemispherical, that can be observed. We can't go underground. That would be the God view again. We only have our view on the flat plane, and we can measure the rise and set angles of all these different luminaries. There was the whole, Bro Sanchez again coming out with his, nonsense that we don't know if that's the moon. We would see, like, you can literally take the modeling programs, you can go out and film it, and you can run them parallel, and you will see that it absolutely is the moon. The way that it was designed, it works perfectly. Again, if you need any more proof that you're in a created reality, then the fact that there are pictures in the sky that rotate around each one of us, right? And there's only one set of each of these observable luminaries. There's only one sun. Jake saying that there's not one sun. Literally, Jaron Campanella, as much as I can't stand his disinformation and what he did, he literally went to Antarctica and showed us evidence of the way that the celestial sphere works in the south. Jaron has that documented. Whether you like him or not, it was a single sun that they observed for 24 hours above them, rotating, right? Above them, not below them. They weren't underneath the ground for any other observer. It all happens from a flat plane, axiomatically. And the way that the elevation angles are always taken in relation to sea level, right? So this whole entire understanding of how the spherical heavens works amongst the latitude and longitude system is mapping and bridging the Cartesian coordinate system with 2 poles, right, Jason? If you can go back to the mole weed.
Okay.
You have to have 2 poles, right? And then you can map a spherical heavens to a flat stationary plane. And this is what we've been able to find. This is the most detailed, specific. If the Earth had curvature, if we could, represent the baseline change, if I went to 10 degrees north or south of Jason, I'm like, yeah, Jason, yep. When I minus my 10 degrees, we are exact. I would say everybody here. And if I could, get gravity and water to stick to a sphere, I would have to say that. But I do know that the ground I stand upon is fixed and flat and it's measured off sea level. I have to take into account how a heavenly body, like the celestial sphere that wraps around us, would map onto the Earth. We need to have boundaries here. How do you create a boundaryless boundary? Like some of the things that people don't ponder, are the questions that they should be. If you're trying to understand how this all works, you need to start to think outside of what you've been taught, outside of what you can think, and start to understand and bridge these things, especially if you can follow along with the scriptures when they talk about bridging the heavenly with the earthly, parabolically and literally through this virtual reality. What Jason's got, this is one of the best. So when you pivot and adjust, Jason, with your angles here and you zoom in, what you've done, see, look at that view. Doesn't that just look crazy to everybody? That's a static picture that Jason's got here, and it morphs into so many different there's so many different things that you can see here. You can have curvature if you want to say it's curved. It's literally a flat plane where Jason's merged the heavenly and the earthly. And now what we have is those, Andrew Marsh data points of a fixed flat plane where north, east, south, and west are directional azimuth measurements around us with sea level. And what you now have is the baseline staying the same. The heavenly luminaries showing you if you stand on that meridian point or that point between longitude and latitude where this city is, this is absolutely what you would measure, right? You don't measure the curvature. You go ahead.
No, I'm just going to say that this is the prime meridian on the equinox. And so we're at the North Pole and the sun's doing circles at the horizon right here. It's flat to the horizon. But at the very same time on the same day, right, you have a person at 80 degrees north that's going to see the sun 10 degrees above the horizon. At 70 degrees, you're going to have the sun be 20 degrees above the horizon. At 60 degrees, it's going to be 30 degrees above the horizon, and so on and so forth until you get to the equator, where you'll have the sun being 90 degrees, right, at the equator. And then it's just going to go the other direction to the south. This is all the same day, same time. Everybody on the prime meridian, everybody seeing the sun at these elevation angles. The baseline never changed, right? But the tilt of the equatorial plane has tilted based on your latitude.
And this is how we navigate. This is how we're able to know where we are on the map, right? Where we are due to where the sun is, the sun's position and the sun's direction. And then at night, we can use the stars. That's how we navigate through this reality.
Absolutely. All right. Well, let's do a quick summary here. Bring up the slides that we were going through before. And just show everybody again, there's 6 conditions of resolving failure. So all of these, you have to have passing grades or the measurement fails the first time any one of these fails. So the angular size, the angular resolution, the brightness, remember you got the inverse square law, diminishing the brightness of the light, that cuts things off real quick. You have contrast. Contrast we've seen is a huge reason why we can't see more than 125 miles, because contrast extinction. Then in all the environmental factors, these just make all the observations shorter and shorter. You got to have overlapping circles of sight and no obstructions in the way. All 6 of these things have to be passes in order for something to be resolvable. Any one of these things fails and it's no longer resolvable. So there's so many things to think about. Like if you're imagining being able to see something more than 125 miles away, you have to ask yourself, well, how big is it and how far away is it? Because that's going to tell me the angular size. All right. What am I watching it with? Am I going to be able to resolve it? Is it going to be bright enough? Is there going to be enough contrast left? What are my environmental factors? And are they within each other's circle of sight?
Yeah, it makes you wonder how science, these crazy people that tell you that they can see so far, the distances that they purport. Again, how large would an object have to be if you could see the light of it from trillions of light years away? And
no, we can figure it out. We can figure it out, and it's unresolvable. It is.
And the other thing that they try to sneak in is that it's a different time period. Oh, that light that you're seeing there is like thousands of years old, right? When again, everything in reality is happening in real time. You imagine it's in a game, there's a clock, there's a speed, there's a playhead to reality, and the sun is basically that. So we're all on, real time.
I got one more thing. I asked ChatGPT
To add
what like the human eye, what star is the farthest the human eye could see?
Okay.
And it's saying a very solid naked eye stellar example is Eta Carinae, roughly 7,500 light years away.
I wonder if that means something dog. But so 7,500 light years away. Okay.
Like,
tell me more.
Right. And then there's these other examples. Then it says an even more extreme historical case, Andromeda Galaxy reached roughly 6 magnitude, essentially naked eye threshold at about 2.5 million light years away.
Yeah, so the Andromeda Galaxy is the closest galaxy to the Milky Way, they say, and it's supposed to be crashing. We're on a unstoppable path to merge together in the heliocentrism reality.
Yeah, so the 7,500 light years, if you're wondering how far is that, that would be 44 quadrillion miles away.
That's how far glurfers think they can see 44 quadrillion.
Yeah, and the 2.5 million light year away example, that you would have, that's 14.7 quintillion.
Wow, quintillion miles now. 14.7. Yes. That's how far Jaren thinks he can see, or Muktoon thinks he can see 14.7 quintillion miles. I mean, don't they wear glasses? Aren't they like, I mean, you can.
How bright would that light have to be?
And how large to be seen?
And how large?
Actually, yeah, you would multiply it by, I'm not the best at math. I'd leave that up to you.
You can let ChatGPT figure it out. It does it better.
The reverse square law of that.
This is the Globers. They think they can see quintillions of miles when the truth is you haven't seen anything more than 125 miles. Sorry.
Yeah, the contrast is gone. Any of those 6, can we go back to the slide again one more time, please? That's funny. Yeah. 14.7. Yeah, I can see about 14.57 quintillion miles with my eyes. Most amazing creation the creator ever made, right? Here we got the 6 conditions of resolving, and that's not, victory. It says failure, right? Failure. These things, any one of these 6 things can stop us from making observations. That's why, if Earth was flat, we'd be able to see the Eiffel Tower from, New York, or we should be able to see the Statue of Liberty from Newfoundland or Quebec. They'll say some of the craziest stuff. Well, how about we talk about what the contrast is going to be over how many miles, or the brightness of the object. So I was the one that started saying back in the day when everyone was doing tests, that if you want to have the longest distance observation, what you need to do is have a very large mirror, right? Some pretty high elevations. You need a mountain. And if you go and have someone at a very, very, very far distance and you shine the mirror, there's a good chance you're going to see that flash. And nobody really took me up on it. Oh, and one more thing, Jason, before you go, I just have one more thing. There's been a bunch of people like Owen Benjamin and all these characters, David Weiss, talking about experiments, right? Jason and I have said, Owen anyone out there that has the capability, has the funds, all you need is a lake or an ocean where you have 3 miles of land along that waterfront where you can either dig a trench, right, and fill it up with water, right, and see if at one end the trench is an inch higher or whatever the distance is at the other end of the trench, or you could have surveyors and you can actually stake it out, build a sort of wall across that 3 miles with a water level. Jason, I don't know if you've heard about anybody talking about flat earth experiments. Well, if you want to do one to prove the earth is flat, all you need to do is build a water level that's 3 miles long and have a surveyor check the points all along. I've heard such crazy, Jason, they're trying to do things that are not going to give you the correct results, right? Anytime you have to take into effect also that things get smaller. Jason, do you have that slide on an angle? Oh, there you
Yeah, so we've used this model before. This is in motion. It's a 3D modeling program. And so we've got a surveyor here, and I've got a bunch of surveyors going off into the distance. I put this lighthouse in here. Let's go ahead and change the position on this lighthouse. We'll bring it in closer. And you can see here. All right, so we'll start moving it away. And what's going to happen to this lighthouse as I keep moving it away?
remember, this program's a flat plane, everybody. There's no curvature.
It just keeps getting smaller and smaller and smaller. And I can just keep scrolling this out until it becomes unresolvable. All right, it'll get down to the point where no pixel is left to be shown anymore, and it's just fully dissolved. All right, so I bump this out to, it's way out there, and yeah, it's gone. But I can bring it back in. You'll see it. Let's go around here. That's still pretty far away. Right here, you might be able to see it if I... Nah, it's still too far. Still too far. Let's bring it into there. So now when you can see there's the top of the lighthouse and the light beam right there. But here's our surveyors. Now here's an orthographic view. This is the way Globers believe the world operates.
This is what they see.
Yeah, so all these guys, they're farther and farther away, but they're all the exact same height. This is like a cartoon. There's no perspective applied. Here's our picture of the lighthouse. This is way far away. If I bring this back into a perspective mode, you can see it's way back there.
Yeah, this is the real mode that we see in, not the orthographic one. It's a great demonstration.
Things get smaller with distance.
Absolutely. Sorry, we don't see too far, but we wanted
they're
to.
Unresolvable. Yeah.
You know, it's not about.
We see to the limits of light, and that's it.
Well, all the limits. Add them all in. The algorithm set, the way that it all works, the distances. This was a good experiment. Hopefully, people can start to understand. Like even looking at the colors. If you can zoom up in the air, you can only see a little bit of pink and then maybe a little bit of yellow here. But as soon as we rise in, now I can see red, I can see purple, I can see green. You can see more and more of the color, and you can see it's a flat plane. But yet we lose different squares of the color due to the way that the perspective works with the horizon 1.22459, right? Squared times the height of the observer, right? That's how we measure to this vanishing point. This is what we've been trying to show people and share. See how the colors are disappearing? The contrast is taking away what you're able to see. And then all of a sudden, so we can still see some green. We can see some, it's like a fuchsia pink kind of color, purple. But as you move further back or down, you see less and less. Soon it'll be only, teal color that we can see. And this is how our eyes and everything actually works in reality.
That's it. exactly how it works. 3D Cartesian perspective with limits to light, right? It has to be resolvable. That means there has to be enough contrast. There has to be enough light, and enough angular size, all that kind of stuff. This is on a flat plane where there is no occultation, nothing to get in the way.
That's right.
But yet things will get too small to resolve. You cannot see forever, even on a flat plane, everybody.
That's right.
All right. Anything else that you want to cover, brother?
No, make sure you're tuned in. I've got a Rumble channel. The description, or no, in a pinned comment below this live stream, you'll see a link to it. There should be a Rise and Grind. We'll get a morning show in tomorrow with some brand new music. And stay tuned. Again, Sunday night, we're going to talk about the 12 mansions or houses in the sky that's modern day, constellations. We're going to look at them. We're going to talk about where they are, what they first were called, right? And look at that a little bit. A lot of it's still pretty much the same. So make sure you're tuned in. That'll be here on this channel. Stay tuned. We got a lot coming up. We're really looking forward to as we move into the, second part of the dog days here.
Absolutely. Well, where's the only place people are going to get this content, brother?
Only on the Hawashai News Network.
Another wasted night with your hands not tied to mine.